So, hi everyone. So, today we will start our ninth tutorial class. Okay. So, in today's class, we will be mostly discussing, continuing a discussion on the specific heat and like first discussion will be on specific heat, and from there we will be calculating different things like equilibrium constants in a reaction and the problem regarding this. So before starting our discussion, let me let me first revise the thing that we have discussed in the previous class. Okay. So in the previous class, we have started our discussion from uh, electronic contribution to the partition function. Okay, so as you know, on the energy scale, first comes the translational partition function that is always there in normal room temperature. Now the energy scale of other the energy scale of other contribution like rotational, vibration, electronics. So for the case of rotational, if the molecule becomes not a linear molecule, like not a monoatomic molecule, if it's a diatomic molecule, linear, non-linear, whatever the case is, then in that case the rotational contribution to the partition function will be exist there. And if you move far into the energy scale, then comes the contribution of the vibrational, and the electronic comes much more beyond that also. Okay, so that means the electronic contribution. So first we discuss the electronic contribution. So we discuss that uh, the energy separation is usually very large in the case of electronic case. Okay, so that means so if you write the partition function for the electronic contribution, Q equal to summation of the energy levels E Gj to the power beta Ej. So so the energies are so large. If you if you just write this thing in terms of series, it looks like this: Q1 to the power beta E1 plus J2 to the power minus beta L2. The energy like E1, E2 are so large, so these contributions are basically becomes negligible. Okay. So the only contribution that comes is from the degeneration of ground state, right? So that we have discussed. Okay. After that, we have discussed about the what is the total partition function formula. So total partition function Q simply takes the form Qt into QR into QV into QE. Q is the total Q tot, you can write total partition function, and these are the basically different contribution, like T is translational, R is rotational, P is vibrational, and E is electronic. Okay. So these are basically different contribution of the partition function. Okay. Now second thing is, now you can write, that means, so we have already known what is the expression of the partition functions, right? So you can write the Q dot in terms of the explicit expression of the individual partition function contributions, right? So the first translational partition function, the expression is V by lambda Q, right? That is the case of the partition function when a gas, let's say, trapped inside a volume V, then its translational partition function is simply V by lambda Q, while lambda is thermal wavelength, right? Now comes the rotational. So for rotational, we know it's T by sigma theta, but theta the rotational temperature, T is the temperature of the experiment, and sigma is the factor. Okay. So for case of heteronuclear, if the molecule is heteronuclear, we know sigma takes the value 1. For case of homonuclear molecule, sigma takes the value 2. Okay. Next come the vibrational. So vibrational partition function has this kind of form, 1 by 1 minus e to the power t theta v. Now here in this case, theta v will be its corresponding vibrational temperature. This is similar to the almost similar to the case where we have defined the theta r as rotational temperature. Okay. So here the case, the theta v is the vibrational temperature, and last comes the electronic contribution. And as you know, for the electronic contribution, only the degeneracy of the ground state is only contributing into the total partition function. So the electronic part would be simply G. Okay. So this is the Q total, the total partition function. Okay. Now after this, what you want to do is that you want to calculate the mean energy of the whole system. Okay. So what you have done, so the mean energy E is simply 1 by Q by del Q del beta constant volume, that we have derived from our previous discussion, that you also know, right? Now here in this E, there's a minus sign there. Okay. So E would be simply summation of E translational, E rotational, E vibrational plus E electronic, right? So what we have done, we have first calculated the translational contribution to the mean energy. So that is the ET basically. So ET is simply 1 by QT by del QT by del beta. So we know Q translational is V by lambda Q, right? So if you substitute QT here into this expression, you will be getting the value of ET as half KT. So here what we have taken, not half KT, it would be 3 by 2 KT. 3 by 2 KT. Okay. So the thing is, whether it will be half KT or 3 by 2 KT is depend upon the dimension of the system you are taking. So here, for the case of 3D box, the Q translation will be V by lambda Q in 3D. In case of 2D, Qt would be V by lambda, okay, into D. And for the case of, sorry, not 2D, it's 1D. For 2D, it will be lambda square, right? So this is for 1D. And if you calculate similarly, the ET for 1D case, you will be getting 1 by 2. 1 by 2 KT for case of 1D. 1D. Okay. So anyway, let's take the case of 1D right now for the sake of this discussion. Okay. So let's take ET for 1D case as half KT. Okay. General case you can say. Similarly, next comes the rotational part. So rotational would be ER. Similarly, 1 by QR by del QR by del beta at constant volume, right? Now similarly here the QR expression would be so QR, we have a very cumbersome expression. It looks like this. QR is 1 plus 3 to the power 2 beta HCB plus 5 to the power minus 6 beta HCB dot dot dot. This is basically a series term is here. Now for the case of calculating the ER, so ER if you calculate, it basically gives you this kind of expression. It's there will be a series here, there will be another series here. Now what we consider, that we have considered the linear case, the linear rotor, the molecule as a linear rotor, and we have considered the temperature of the experiment is much more higher than the theta, the rotational temperature. So for that case, we can simply write the E rotational as, if you calculate, it will give you 1 by beta or kVt, the expression coming from ER. For case of high temperature, the linear rotor gives you this expression. Now, for the case of non-linear rotor, the expression of ER would be simply 3 by 2 kVt. Okay. This is the case of the non-linear rotor. Okay. Now last comes, not the last actually, the vibrational energy. So for the vibrational contribution, we write the EV. The vibrational contribution is simply similar 1 by QV into del QV del beta at constant volume. Now here QV is 1 by 1 minus to the power beta HC nu tilde. Nu tilde is basically the what is called this wave number associated with the modes of vibration, right? So a molecule, let's suppose a three atomic molecule or 4 atomic molecule is there. So there will be different modes of vibration will exist in the molecule. So if you like raise the temperature high enough, so there is a wave number that will be associated with each independent modes of vibration. So that modes are basically, the wave number of that modes are basically denoted by nu tilde. Okay. Now, similar way, here also if we substitute QV here, vibrational case. So, to do the calculation, EV, when the temperature is much higher than theta V. Similarly here also, in that case, the EV would become just kBT. Okay. The case of high temperature, T is very greater than theta, similar case. Last comes the electronic contribution. Okay, so electronic contribution is like you can say the QV, the expression of QE, sorry, is simply G0. That means the degeneracy of the ground state. Now this is just a constant value, right? So for this case, if we calculate this del QE del beta constant value, this simply gives you 0, right? So the contribution of the electronic partition function into the mean energy would be simply 0 unless you make the temperature very high. Okay. So this is the thing. Next thing that we've discussed is the specific heat. Okay. So specific heat or heat capacity. So heat capacity. So we will in this tutorial we will further extend this discussion. So in our last lecture we have discussed the CV, the specific heat at constant volume. Sorry, the normal specific heat means, let's suppose C. Let's just not classify it into different categories. Just take the general definition of a specific heat. So before classifying it, let me just discuss the what is basically a specific heat or heat capacity means. So that means that if you want to raise the temperature, the amount of heat dq that is required to raise the temperature of a substance by amount dt. If you know that two things, then dq by dt will gives you a specific heat. Okay. Now there are two types of specific heat. One is a CV, specific heat at constant volume, dq dt, constant volume, and Cp, the specific heat at constant pressure. So that is dq by dt at constant pressure of volume. Now for the case of constant volume, we know that dq equal to du plus pdv, right? Now this is we know from the first law. Sorry, second law. No, it's first law actually. It's second, first law. Yeah. So for first law, this is we know. Now, if you take volume constant, this term is 0. So dq equal to du. So you can rewrite this Cv as du by dt at constant volume instead of dq, right? So now the thing is, so that means that if you know basically if you know the what is this called the mean energy of a molecule, okay, mean energy of the molecule, then you can calculate the total the specific heat or the heat capacity of the system. So if you calculate the mean energy is E is basically nothing but U equal to U, right? So if you know this, then from this you can easily calculate CV is N is the number of molecules delta E by delta T at constant volume, or delta E average means the mean energy, which is nothing but equal to the internal energy, which is just the addition of translational, rotational, vibrational, and electronic contribution. Okay. So if you add all this contribution, that gives you the total mean energy, and from that total mean energy, you can easily calculate specific heat at constant volume. Right? Similarly, you can also, for the sake of the calculation, you can write the CV in terms of beta also. In that case, the expression will be looking like this: del E by del beta at constant volume. So this is the thing. Okay. Now, uh, now there is also a formula exists. So in case of ideal gases, there is a relation between Cp and Cv exists there. So the thing is, if you know Cp, using that formula you can calculate the Cv. Okay, that formula is Cp minus Cv, that you know actually, into Nr. N is basically the mole, number of moles. This only exists for ideal gases. Okay, ideal gases. Okay, so this thing we already know. So that means that now in this class we will be doing some problems, and first we discuss the theory, then we will do the problem. So where we will show that if you know how can you calculate the specific heat if you know the what is this called, the mean energy. Okay. Uh, so we'll start the case. Okay. So for that, okay, one second. Okay. Total specific total. So as we discussed, so the specific heat depends on translational plus rotational plus vibrational and electronic energy contribution. Okay. So, so what does that mean? That so so that means that all the four cases you have to calculate, okay, in order to calculate the specific heat. Now, for the case of translational, you already know that translational component is always there. Like in case of room temperature, also the translational energy is always there. So translational energy is always there in a room temperature. Okay, and you know the EM, the ET, sorry, The translational contribution is simply for the case of uh, for the case of what is this called 3D gas, the ET is simply 3 by 2 kT, right? So if you know ET equal to 3 by 2 kT, so then that means specific heat C uh, specific heat at constant volume CV is at rotation, so CVT, let's write it like this, equal to N into Na. Let's suppose for the case of 1 mole, okay, Na equal to del Pt by del T. So it would be Na into 3 by 2 K. So Na into K would be R, right? So 3 by 2 R. Okay, so basically, so CV basically that means is, so CV is basically del E by del T into Na. So that means Na into del E by del Et by del T plus del E rotational into del T plus del E vibrational into del T plus del E electronic into del T. Will be like this, right? So CV would be CVT plus CVR plus CVB plus CVE. So the specific heat has 4 contributions right there. Okay. So we checked for translational, the specific heat contribution is for 3D case is simply 3 by 2 R. Next, we took the rotational energy contribution. Rotational energy. So for the rotational energy contributions, the expression is very high, very cumbersome, normal expression. We will first consider the limiting case where the temperature is very high and the molecule we are considering is a linear rotor. Okay. So first take that limiting case. Okay. So and check what is the value of this rotational specific heat. Okay. Okay, so let's do it. In this case, so that means CVR would be Na into delta of ER by del T, and ER expression is simply 1 by QR into minus 1 by QR del QR del beta. We know this thing, right? Um, for the case of linear rotor, so let me write it here. So for the case of linear rotor and high temperature. High temperature means when T is much greater than the characteristics rotational temperature, right? So that is defined as theta R here in our discussion. So if the molecule is a linear rotor and the temperature of the experiment is very high compared to the characteristics rotational temperature theta R, so in that case the QR, the rotational partition function, simply takes the form as 1 by sigma HC beta into B, right? Or you can write it as T by theta R into sigma, right? So here theta is the characteristic rotational temperature, T is the experimental temperature, right? Now if you substitute this into this expression of the mean energy, rotational mean energy, you will be getting ER would be simply as kVt, right? So now, so that means CVR would be K into Na, that is R, okay. But this is the case we have written for linear rotor, not for, if you, let's suppose the, if instead of linear, it's let's suppose there's a non-linear rotor is there, okay. So for non-linear rotor, similarly high temperature case, okay, if the non-linear rotor is there, for non-linear rotor, the ER is, we know that, the ER would be 3 by 2 kVt, right? 3 by 2 kVt. Okay. So now, if ER is 3 by 2 kVt, then the CVR would be 3 by 2 R, right? So this is the expression of specific heat, right? So, okay. Yeah. So this is the case for the non-linear rotor. Okay. Now what happens when the temperature is very high? Now, because this cases we have considered so far is only when the temperature is very high. Okay. Now let's take the situation where the temperature is not that much high. Okay. So the temperature is not high. Okay. So for if the temperature is not so high, in that case, we know that the energy, the rotational energy term, will take a big expression, that is this big conversion expression, HCB into 6 into e to the power minus 2 beta HCB plus 30 into e to the power 6 beta HCB plus, then it's this whole thing is divided by 1 into 3 into the power minus 2 beta HCB plus some higher order terms. So in that case, you have to take the derivative of this whole thing in order to get the expression of the specific heat, okay, which is this del ER by del T, okay. So you have to substitute this ER into this expression of CV, yes, specific heat CV, in order to get the rotational contribution, right? So this is the case when the temperature is not high, okay. And last comes the vibrational case, okay. So for the case of vibrational, okay, so as you know, from the energy scale of different contribution, the vibrational contribution will be only be activated when the temperature is very high. So in that case only the vibrational modes will become excited, right? So we know that in general the expression of these vibrational energies is given by this EV, the mean energy for the vibrational contribution EV is simply Hc nu tilde by e to the power beta Hc nu tilde minus 1. So this is the general expression of the vibrational energy. Now, if you calculate the CVV, okay, one V denotes the constant volume and another V. So let me write this V as a curly V, just to avoid confusion. And this V is the vibrational V. Okay, so then the expression would be looks like Na into del EV by del T at constant volume. So if you substitute this expression of energy, mean energy, then you will be getting CVV as theta V. So you have to use the expression of theta V. So theta V is nothing but K into HC mu bar. Sorry, my internet. HC mu bar by K. This is the expression of K is a Boltzmann constant. Okay. So this is the expression of basically the vibrational temperature. Okay. So the thing is, so if you do the derivative, it will looks like this: theta V by T whole square into e to the power minus theta V by 2T minus this whole thing will be squared, e to the power minus theta V by T, the whole thing will be squared. So into R. Okay, it's Na into K. So now next is so what happens if you take the energy, the temperature is much higher than theta V. So in that case, CVV would simply takes the value R. Okay. So these are the like different cases, the different contributions and different temperature limits that has been shown by the specific heat. So now if you want to do a summary of from whole of this discussion, we can write that for translational case, the specific heat has the value 3 by 2 R, and the rotational part will be can either having R or 3 by 2 R. R would be for the linear case and 3 by 2 R would be the non-linear case. Okay. And for vibrational it would be just R, and that is only to when all the modes are activated. All modes activated. Okay. So that is like the different contributions. So we can write this whole thing, okay, in a formula, in a formula expression, formula like expression. So CV is the translational part is 3 by 2 R, and the rotational part is simply either it is so you can write it like this: mu R by R by 2. Okay, so so nu R would be 2 in case of linear, and nu R would be, so nu R star, let it like this, and nu V equal to R. So we can further simplify it and take half as common: 3R plus mu R star plus mu V by 2 into R. Okay. So where nu R is 3 for non-linear and 2 for linear, and nu V is 1 when all nodes activated. Right. This is the simply the expression of the specific heat of point. So now we'll do some problems. Okay. So the first problem is This is the general expression here. The first problem is, let me write. Estimate the molar constant volume with capacity of CO2 gas at 500 Kelvin. Okay. So, so CO2 gas. Okay, so we have to find basically for a CO2 gas, what is the molar heat constant per volume. Okay, basically CV. CV you have to calculate at 500 Kelvin. Now the thing is here. So CV we know. Basically, we will ignore the electronic part for the time being. So you'll be considering the translational, vibrational, rotational. So here in the problem, the rotational constant, the B basically is given here. The rotational constant B is basically given as 0.39 centimeter inverse of plane. So now, the thing is, so first thing you have to see, first thing what you have to calculate is the translational part, right? So as you know, the CV translational CVT basically is simply 3 by 2 kVT. Okay. This is common, right? This is, let's suppose, a 3D system. Definitely, CV translation will be simply 3 by 2. Sorry, 3 by 2 R, not kVT. 3 by 2 R. Next comes the vibrational part of it. Sorry, rotational part. This is the translational. Now comes rotational. Now for the rotational case, we know carbon dioxide is simply a linear molecule like this. Okay, now as it's a linear, it's just a linear molecule. Okay. as we need it's a linear molecule, and so we can basically use the fact that for a linear molecule, what is the contribution of the rotational specific heat, and also we have to calculate the theta, because theta, like in order to use the formula, you have to make sure that the temperature of the experiment should be greater than the characteristic rotational temperature. So theta you can calculate basically using this HCB by KT kV. So B is already given, B value 0.39 centimeter inverse. So you have to show that T should be greater than equal to theta r. Okay. So if it is linear and T greater than equal to theta r, so that means we can write mu r star equal to 2, right? So that means the rotational part, so CVR, rotational part would be simply R. Okay. Because 2 by 2 cancel, so you get only R. Okay. Lastly comes the vibrational part, right? Now, similarly here also, you have to check the vibrational part. So for vibrational part, you need the frequency, or the what is this called, the wave number of the modes of vibration. Okay, so from there you have to calculate theta v. Okay, theta v is simply hc nu bar by k. So let's think there are multiple modes of vibration are there. Suppose one mode has nu 1 bar, one mode has nu 2 bar, one mode has nu 3 bar, like this. So you have to make sure for all the cases these modes are basically active. So active modes means basically that means the temperature of should be greater than equal to theta v1, theta v2, theta v3. So like this. So if for all the cases the temperature of the experiment is greater than the characteristics vibrational temperature corresponding to the frequency modes, so that means that particular mode or all the set of modes are basically activated. Okay. So like this, if all the modes that is associated with the molecules are activated, for that case we can write the C V V, that is the vibrational part, is as R, right? You can take nu V star equal to 1, right? That we have discussed earlier for the case. Uh, yeah, it should be 2 here, not 1. Now it's fine. Yeah. So, so if all the modes are activated, all modes are activated, so for vibrational case, CVV is simply equal to R, the when all modes are activated. Okay. So that means the total specific heat CV would be simply the summation of 3 by 2R plus R plus R, right? So 3 by 2R plus 2R, 7R by 2. CV value would be 7R by 2. Okay. The total specific heat and constant volume. Yeah, so it's a CV should be in prefix, not suffix. C, yeah, that's right. Okay. So we got the specific heat. So we'll do another problem like this. So here the problem is estimate the molar constant volume heat capacity of NH3 at 300 Kelvin. So this is the problem. So for NH3 molecule, you have to calculate the constant volume heat capacity. This is CV thing. Provided that, so it's now the case NH3 is basically a non-linear molecule, unlike the previous case where the CO2 was basically a linear molecule, right? So for this non-linear molecule, as it's a non-linear molecule, so there are three rotational constants. Their values are given. So rotational constants are A, that is 9.94 centimeter inverse, B 9.44 centimeter inverse, and C is 6.19 centimeter inverse. So all these three rotational constant values are given. Now what you have to do here from this is you have to calculate the total volume, constant volume heat capacity, right? So how could you do that? So for that, first you have to calculate the translational contribution, right? So translational contribution is simply that is fixed, right, in room temperature. So CV basically depends on CV translation, CV rotation, CV vibration, plus CV electronic. So for the case of translational contribution, so the CVT is always fixed as 3 by 2R, right? That you already know. Next comes the rotational case, right? For the rotational case, what we have to do, we have to first check. So here the thing is the theta r is basically there are three rotational constants are there. There are basically three values of rotational. This temperature would be there: theta r1, theta r2. So for the case, the temperature should be greater than equal to theta. That we have to first verify. And since it's a non-linear molecule, so the rotational contribution CVR would simply takes the value 3 by 2, right? 3 by 2, yeah. Because it's a non-linear molecule, right? As it's a nonlinear molecule, the CVR is simply equal to 3 by 2R, right? Lastly comes the vibrational part. So vibrational parts are the same way. You have to first find out whether all the vibrational modes are activated or not. So for that you have to calculate the characteristics vibrational temperature for all the modes with different frequencies, independent modes. You have to make sure that the T is greater than uh, with respect to all the vibrational modes. Okay, theta V2, theta V3, like this. Depends upon how much vibrational modes exist in the system. Temperature should be higher than all their related characteristics vibrational temperature. And if this thing is true, then we can write we can consider all the modes as activated, and we can take the gamma B star in this formula as equal to 1. So that makes the CVV equal to R. Okay, right. So in that case, if this is what it is true, then you can write CV equal to translational contribution 3 by 2R, rotational contribution 3 by 2R since a nonlinear molecule, and vibrational contribution R. Now we can sum 2 into 3 plus 3, 6, 7 R by 2. Previous equals, so let's take the side. So it was 4, right? So um, so this should be not 8 R, right? So this would be 4 R, yeah. So this case CV would be simply 4 R, right? Okay. Let me just recap. So when in a problem, if at a certain temperature, if it has been asked to calculate a specific heat at constant volume, so what you have to do, you have to first check whether the rotation translational part is very simple. It's simply 3 by 2R. If in the problem is very explicit about a dimension, then you have to write, you have to use the CVT according to it. But otherwise, in mostly cases, the translational contribution is simply 3 by 2R. In that case of rotational case, so for that you have to check whether the molecule is linear or non-linear. So for the linear case, you, you can take the new R star as equal to 2, and if it's a non-linear, just like the second example, you have to take the new R star, basically this thing here in this main expression. This is new R star. For linear case, you can take it 2. For non-linear case, you have to take 3. Next, the vibrational case. Now, for the vibrational case, it depends. You have to check whether all the vibrational modes are activated or not. For that, you have to calculate. You have to make sure basically the temperature of your experiment is much higher than the corresponding vibrational characteristics temperature for that particular mode. And if that is true, you can consider all vibrational modes are activated, and you can take nu V star equal to 1, which makes CVV equal to R. Okay, R is just the ideal gas constant. So which makes the CV value is equal to 3 by 2R plus R plus R. So 3 by 2R plus 2R, 7 by R. And next problem, we took the similar type, but here the molecule is non-linear. So for that, we also similar we have calculated, and we got the value of CV as 4. Next, the last type of problem. Estimate the constant volume heat capacity of H2 at 100 degree centigrade. Okay. Here the vibrational wave numbers are given. The vibrational wave number is basically uh, so vibrational wave number is nu tilde is 17.3, and since H2 is a non-linear molecules, so its rotational constants are given. So rotational constants of H2 molecule is given by 27.9, 14.5, 9.3 centimeter inverse. So these are all centimeter inverse. Okay. Now what we have to do here, the translational case, it's always simple. CVT is 3 by 2R. For the rotational case, you have to check theta r values. 3 theta r values will be there. 3 rotational constants are there. So theta r1 will be HCA. Let's suppose the first constant as A by Kp. And if you put HCA simply 27.9 by K, it values gives you 40 Kelvin. Theta R2 similarly, if you calculate, gives you 21 Kelvin, and theta R3 gives you 13 Kelvin. So T is greater than theta R1, theta R2, and theta R3, right? So since T is next you have to check theta V value. So if theta V value is greater than T, then gamma V star will be 0, and if theta V is less than T, then gamma V star will be 1. Okay, so depending upon that, we can calculate the CV. Okay. Now, the last problem. Consider system with energy levels as Ej equal to G and in molecules. Then you have to calculate A. Show that if mean energy per molecule is AE, then the temperature is given by beta equals to 1 by E log 1 plus 1 by A. Okay. Next, you have to calculate, evaluate the temperature for a system in which the mean energy is E, taking E equivalent to 50 centigrade. The P is calculate the molecular partition function Q for the system when its energy is AE. The third thing is show the entropy of the system is S by NK equal to 1 plus N non 1 plus N minus N. Okay. These are the things you have to do. First thing is the energy is given is energies are basically of the system is Eg equal to J into E. Right. So that means basically the energies it looks like this. Ej is JE, so it just looks like this. J takes the value 0, 1, 2, 3. So it's like 0, E, 2E, 3E, and so on. This is how the energies, it's a kind of a ladder, energy ladder where each energy are separated by the same amount that is needed. So in that case, first thing is it's asking that if the mean energy of the molecule is AE, then the temperature is following expression of the temperature. You have to prove. Okay, how to do that? So for that, the thing is we have to first calculate the partition function. So partition function Q is summation over j e to the power beta Ej. So it would be then summation over j e to the power beta j into E. So it would be then j takes the value, starts from 0, 1, 2 like this. So that means it would be starting from e to the power minus beta into 0 into E plus e to the power minus beta 1E plus e to the power minus beta UE and so on. So we can write this is as 1 e to the power minus beta E plus e to the power minus beta E whole square plus e to the power minus beta E whole cube, and like that it goes on. Q expression would be looks like this. Now if you do the summation of this infinite geometric series, you can write this whole series in a closed form, which will looks like this: 1 plus 1 minus e to the power minus beta E. This is basically the expression of the partition function Q. Now from here you can easily write the mean energy, that is given by minus NQ del Q del beta at constant volume. If you do this, then so 1 minus beta E, so 1 minus beta E is outside, so that will gives you minus 1 minus beta minus beta E. Now del beta of 1 by 1 minus e to the power beta E minus beta E. You have to do the derivative here. So mean E would be simply minus 1 minus e to the power minus beta E into minus 1 to the power outside 1 minus e to the power minus beta E whole square into minus e to the power minus beta E. So this would so this one term from the denominator will cancel. E is outside, so it would become E into e to the power minus beta E. Denominator will be 1 minus e to the power minus beta E. So that is a mean energy expression, right? Next is so the mean energy from the problem, according to the problem, the mean energy is nothing but AE. Okay, so we just simply substitute the mean energy here. So that gives us A equal to E to the power minus beta E by denominator 1 minus e to the power minus beta E, right? So from here, what we can do, E will cancel. You can write this e to the power, you can write this as, you can simply flip both the sides. So 1 minus e to the power beta E by e to the power minus beta E 1 by A after taking the inverse. So now it will gives you e to the power plus beta, right? So it will go upside, minus 1 equal to 1 by A. Now here, from here you can write e to the power beta E as 1 plus 1 by A. So beta E would be log of 1 plus 1 by A. From here beta is equal to 1 by E ln of 1 plus 1 by A. So This is the expression of beta that we have been asked to find out, and we're getting exactly the same expression. So that means the first problem has been derived correctly. Now we move to the second problem, the B. So problem B, in problem B, it has been asked that calculate the molecular partition function Q for the system when its mean energy is A. Okay. Basically, so that means what we have to do, we have to basically write the partition. We have actually a expression of the partition function here itself, but in according to this second question, you have to write this expression of the partition function in terms of A and E. Okay, function of A and E. Okay, because here there's no A terms is involved here, right? So you have to basically rewrite the partition function in terms of A and E. Okay, so how would you do that? So for that, we already know the partition function expression, right? So let me rewrite it once again. So Q is simply one minus e to the power minus beta e, right? This is the form of Q that we have derived earlier, right? Now from here, uh, what we can do here is that uh, the mean energy is A. So from here, what we can do, we have done it this, we have taken A equal to 1 by Q delta Q del beta is minus and at constant volume. So after doing that, we got this expression beta equal to 1 by epsilon ln 1 plus 1 by yeah. So now what you can do here, you can further simplify it. You can make it beta equal to ln 1 plus 1 by A here. Now from here you can write e to the power beta equal to A plus 1 by A, or e to the power minus beta equal to A by 1 plus A. So now we got this e to the power beta A in terms of A. Now from this thing, what we can simply do, you can just put e to the power minus beta A in terms of A into this expression of the partition function in order to get the partition function expression in terms of A. So Q we can simply write as 1 by 1 minus A by 1 plus A, which makes the whole thing as 1 plus A minus A by A, 1 plus A. This makes the thing 1 plus A by 1. So something is wrong here. Yeah, this is e to the power not, this is e to the power minus beta, right? It is e to the power plus beta, but I find out actually, e to the power plus beta. So when you substitute it as e to the power minus beta, then it will take the form 1 minus, so this is something of the case. This is the case e to the power beta in. So if you do substitute this, so now it 1 minus A by A plus 1, e to the power minus beta A would be A by A plus 1, right? This is 1 multiplied. So A by A plus 1, right? So now it will give you uh, 1 plus A. So Q is basically giving you 1 plus A, right? Okay. So Q give you 1 plus A. Now if you substitute this thing equal to 1 plus A into this expression, uh, so Q is 1 plus A is basically the answer itself. So this is the expression of the partition function in terms of area. So by using the mean energy, we can rewrite the expression of the partition function, that is the main thing that has been asked for in the problem. Lastly is that you have to calculate the entropy of the system and you have to show this particular form of the entropy, functional form. This form of the entropy you have to show. So for that, first what you can write the expression of entropy at first. So write entropy, problem C, entropy as U minus U0 is the difference of internal energy with respect to the absolute zero temperature internal energy, U minus U0 by T plus E ln Q, right? Q is the partition function of it. Here, entropy of the system, yeah. So that's why you have to use the ensemble partition function of the ensemble or the whole system, right? Not for a particular molecule. Okay. So for distinguishable particles, we can write this partition function for the ensemble for the molecular partition function, right? And that is Q equal to Q to the power n. So what you have to do is S equal to U minus U0 by T plus K into ln Q to the power n, right? Now from here, just do the math, just do the normal math. So here, from here you can write S equal to U minus U0 by T plus Nk ln Q, that you can write further S by, you can, since in the proof section you have to ask to prove S by Nk. Okay, so we can take Nk as common from the right hand side, so you can put Nk in the denominator and the whole thing will become then U minus U0, as the Nk term will come here in the this denominator here also, so Nkt plus ln Q, right? The Nk term taken it as common. So now S you can write, this is nothing but a mean energy E by Kt plus ln Q. Okay, Kt is nothing but beta, 1 by Kt is nothing but beta, and mean energy you already know is Ae, so you can write S as Ae beta plus ln Q. Q you already know, Q expression you can write in terms of A, that is 1 plus A you can write, so 1 plus A. Okay, so from here what you can do, this is S by Nk, S by Nk S by NK, then write it as ln ln 1 plus A. So we can write actually E beta, this thing you can write, right? This thing E beta equal to ln 1 plus 1 by E2. We can substitute basically that thing here into the expression. So A plus E beta is ln 1 plus 1 by A. So that gives A into ln plus A by A plus ln 1 plus A by A. Then you can take ln 1 plus A as common. So this whole thing then becomes NK and 1 plus A into ln 1 plus A minus A ln A. Okay. So this is how you will be getting the expression of the entropy. This by NK. Okay, so this is the whole problem. So what actually main thing is in this kind of problem. So the energies of a systems are given. So whatever you do, the first thing that you should calculate in this kind of problem is the partition function, because everything starts from the partition function, the molecular partition function. That we have actually calculated at first. The Q is basically we got it as a geometric series. So Q is basically a summation over j e to the power minus beta j e. If you do the summation, you will get a minus beta into 0 into e, beta into 1 into e, beta into 2 into e, like that. So 1 e to the power minus beta e, beta square, beta e cube. So this is a whole, you can say the geometric summation. If you adds up all, the Q expression will gives you this expression. Now from here we calculated the mean free energy, that is this E mean. So E mean is given by basically this. After doing that, we have calculated the temperature, right? From after doing all the math. And next, lastly in the problem B, what we have done, we have been asked to find the partition function. We write the partition function as a function of A. So we simply put the mean energy beta equal to this expression of the partition expression, the mean energy that comes from the partition function, and from there we got the expression of e to the power minus beta in terms of a plus 1, a by 1 plus a, and we substitute that thing in the expression of the partition function, and after doing that we got the partition function as a function of a. Lastly, we have calculated the entropy. Entropy calculating is very straightforward. So we use that thermodynamic definition of the entropy, where capital Q is the system partition function. So we can write the system partition function in terms of a molecular partition function, whether the system is like distinguishable or non distinguishable particles are. So from there, this is basically the mean energy. So put the expression of the mean energy there. We put the expression of the partition function Q there, and after doing all of this, we got the entropy S by NK equal to this expression. So that's how you can get the calculation of the entropy. Next, what we'll discuss is residual entropy. Okay, so let me write. Residual entropy. So what is basically the residual entropy? Uh, so you already know that the thing is um, for a system, it is not possible to have entropy negative, right? You can make the entropy of a system equal to zero at a very low temperature, or you can say at a temperature equal to zero, close to zero. You can make the temperature of the system equal to zero, but you cannot simply make the entropy negative, right? So, what is basically residual entropy is, okay. The definition is if some so so that means that if at t equal to 0, if the entropy is still not equal to 0, so that means at temperature equal to 0 also there is some disorder is exist into the system which makes the entropy not equal to 0, right? So that entropy, that minimum entropy that exists into the system, or the minimum disorder that exists into the system, although the temperature is equal to 0, is basically known as the residual entropy. Okay, this is the minimum disorder present present in the solid even at t equal to 0. The entropy at t equal to 0 is then greater than 0 is called the residual entropy. Okay, yeah. So this is the basically the definition, the formal definition of a residual entropy. Now, how this kind of how basically the origin of residual entropy is coming. Okay, so so the concept of residual entropy is coming. So let me take an example by which I can explain. So the origin of residual entropy. So here what happens? Uh, let's uh, crystal composed of AB molecules. Okay. Now let's say A and B are similar type atoms. Now, such as similar type atom means such as carbon monoxide or nitrous oxide, so not like this. Similar types of atoms. So that means the dipole moment is be negligible. Dipole moment is very small, you can say. Now, for this kind of molecule, let's suppose uh, in the perfectly ordered state, the system orientation looks like this: AB, 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 AB. So this is a perfectly ordered state. Okay. Now sometimes what happens that um, since AB and BA are similar types of molecule, so holding a configuration of AB or BA would cost similar energy, right? So that means if instead of this kind of configuration, there is a configuration like this: AB, AB, BA, AB, AB, like this, it would also cost similar energy, right? Since AB and BA both configuration cost same energy, so both these two types of configuration has the same energy. So that means, so which actually the thing that I want to say that this this introduction of this BA orientation actually gives a disorder, introduces a disorder into the system, which is known as the configuration disorder. Okay. Configurational disorder. Okay. So because of the this configurational disorder, although the system may remains at temperature equal to 0, but as the AB and BA are equally probable, you can say, bonds. So that means at T equal to 0 also there would be some configurational disorder exists in the system, right? So that means there would be some entropy, the minimum disorder that I'm talking about, the residual entropy would exist in the system. Okay. So what would be the value? So at T equal to 0, we know S equal to the entropy, K is ln of W, W is the configuration, right? Now, if suppose there are n numbers of molecules is there, since each molecule can take two states, either AB and BA, so possible number of combination is W is equal to 2 to the power n, right? So S would be simply K into ln. This is happening at temperature 0. Okay, so that means this entropy, if it's non-negative, then this would simply known as the residual entropy, right? So this would become 2 to the power n. So K would be simply here nk into ln 2. Now nk you can write, n is the number of molecule that you can write as a multiplication of n, that is the mole, and Na is the Avogadro number. So n into Na, K into ln r, ln 2, sorry. So S would be nr ln 2. Now for 1 mole of gas, S would be 1 into R, we know 8.314 into ln 2. So this gives you 5.76 joule per Kelvin as the value of residual entropy. Okay, for this kind of AB molecule kind of a system, AB atomic molecule kind of a system, where both the molecules are similar with each other, right? Now, for the case, let's suppose here we consider A, B, both are similar. Let's suppose now a case where A, B are not similar. Let's suppose A and B has a electronegativity difference. Okay, that means the system would be perfectly disordered. Okay, so when perfectly ordered, so that means the system would be like AB, 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 because both A and B there's a electronegativity difference. So if let's suppose B is plus and E is near a minus, so here automatically there would be A, B, minus, plus, minus, plus, minus, plus, minus, plus, like this. Otherwise, if you make B this side and A this side, so this will give you a significant energy cost, right? So this would be the minimum energy configuration at temperature equal to 0, right? Because making any configurational disorder here introduces a significant energy cost. So that means the system will basically not show those kind of configurational error. Now for this kind of system, that means the what you can say, the configuration, that is W, is simply 1, right? 1 to the power n, that is nothing but 1 itself, right? Because only one configuration is possible, that is AB configuration. Now S you can write similar way, K into ln W. So S equal to K ln1. ln1 is nothing but 0, so S equal to gives us 0. So here you can see there is, for if the system is perfectly ordered, so this is a perfectly ordered system. Ordered system at temperature equal to 0, which makes the residual entropy equal to 0. But here in this case, where you got this configurational disorder, although the system is equal to, temperature of the system is equal to 0, because of that it gives a value of this residual entropy which is not equal to 0. Yeah, so this is basically the concept of what is basically the residual entropy is. Okay. Now the next thing that we'll be discussing is the Gibbs free energy and its relation with the it's about equilibrium gas constant K. Okay, how this equilibrium gas constant K is related with the partition function. Okay, so let me write it. Relation of K, the equilibrium gas constant, with Q, the partition function. Okay, now what is basically a K? Okay, so we already knew that, right? So um, for a reaction, let's suppose a reaction like this is happening, A plus into B into C D. Now in this kind of reaction, the equilibrium constant K is written as K equal to C, that's this is the concentration of C, so the product concentration to the power this stoichiometric of constants or values by D by A into B. So this is how the equilibrium constant. Now in actually real chemical systems, this calculating this equilibrium constants gives us a very gives us a rich information, right? So it will be always better to calculate to know how to calculate this equilibrium constant. Okay, so for that we'll be discussing some ways, because if we know the relation with the equilibrium constant k with the partition function q, so that means we can calculate k from q, right? And q we can easily calculate by using spectroscopy, right? If you know the energy separation of a particular system, right? So from there you can easily calculate the partition function q, and if you know the partition function q, from there you can calculate the equilibrium constant k, right? So that is the both that is the main goal of building this relation. Okay, so for that, first what we will do, we will write the expression of the Gibbs change in the Gibbs free energy uh, using the classical thermodynamics. So using the classical thermodynamics, delta G is change in Gibbs free energy at a particular temperature from absolute zero is equal to delta G0 plus RT ln Q. Here the delta G0 is basically the change in G at standard condition. Okay. What do you mean by standard condition? Standard condition means uh, the substance should be pure and pressure should be 1 bar. Okay, this is the standard condition. Okay, so delta 0 is the change in the Gibbs free energy at standard condition, right? So the expression of delta G0 is simply minus RT ln K. K is the equilibrium constant. Okay. Now we also know that from our previous discussion about the Gibbs free energy, you can write the Gibbs free energy in terms of molecular partition function, right? That expression is basically given by G minus G0. This is from our previous discussion. We know that G minus G0, G0 is nothing but the Gibbs free energy at absolute zero temperature equal to nRT ln Q by N. Q is the molecular partition function. Okay. Now in terms of molar Gibbs function, you can write it like this: Gm0 minus Gm0 at 0 equal to minus RT ln Qm0 by Na. So Gm0 is nothing but G by N. N is the mole. Okay. So you can then, after substituting, after using different relation like N equal to N by Na, after doing all of these things, substituting here into this equation, you got this expression of molar. Basically, this is known as the molar Gibbs free energy. Anyway, so what you can do here is for a reaction, let's suppose Okay, so let's consider a reaction that looks like this: A plus B equal to C plus D. Now from here, what you can do, you can simply calculate the change in the Gibbs free energy at standard condition, that is G0 is simply summation over J nu J into Gm0 J. J is basically the partition function. Okay. So that means delta G0 would be C into Gm C into Gm0 C plus D into Gm0 D minus A into Gm0 A minus B into Gm0 B. Okay, this would be delta G0 here. Now, if we compare it with the temperature equal to 0 case, in that case delta G0 would simply become the summation over J nu J G M 0 J0 absolute zero temperature minus RT summation over J nu J ln Q by Na. Okay, that comes from this expression basically. This expression here. Okay. Now from here, if you do further algebra, now at a certain stage you will get this expression looks like this. Equal to delta G0 J0 minus RT into summation over J ln QMJ by Na by summation over nu J. Okay, now from you can write delta G as delta U, right? J comma 0. So that means you can write delta G equal to delta U J comma 0 minus RT ln summation over J Q J 0 by Na to the power u G. This is how you can write the entropy, the Gibbs free energy in terms of a function of Q, and we will discuss about it further more in the next tutorial. So far this is it. So in the next tutorial we'll discuss more from this. So we are almost end of the class, so let me just stop the recording.